Hi everyone, welcome to another linear integrated circuits class. In the previous class, we finished different op-amp circuits and transducers like current to voltage and voltage to current transducer and other type of amplifiers like a current amplifier. Today we will continue with the limitations and practical limitations of op-amp. Mainly, we would focus on the frequency response and the frequency limitations of an ideal op-amp. Before I start the class, do you have any questions from the previous class? No. A quick review of an op-amp. For an ideal op-amp, the input current is 0. V positive is equal to V negative. We have a non-inverting input, and this is the symbol for the 740 watt normal op-amp, and also the terminals of the op-amp. We have the inverting, non-inverting, positive supply, negative supply, and the output, the main terminals of an op-amp. So in this chapter, the chapter objectives of would be first to define the gain bandwidth product and describe its use in circuit design and analysis. The gain bandwidth product determines the frequency response. It's a feature of the op-amp itself, and it's built into the op-amp. We can't change the gain bandwidth product, but there are other ways that we can change the frequency response. We want to determine the upper and lower break frequencies in a multi-stage circuit. And by determining the upper and lower break frequency, we can determine the frequency response. Define the slew rate, power bandwidth, and calculate their effect on circuit performance. Understand the difference between power bandwidth and a small signal bandwidth. Detail the difference between compensated, non-compensated, and decompensated op-amps. Calculate the DC offset and understand how to minimize it. Calculate the DC drift and understand how to minimize it. Discuss which factors affect the noise performance of an op-amp circuit. Calculate the noise voltage of an op-amp circuit, and analyze the common mode rejection ratio, signal to noise ratio, and so on. So frequency response. What is the frequency response? The majority of this chapter would be around the limitation of an op-amp, specifically the frequency response, the frequency limitation of it. So the frequency response is the frequency that the op-amp operates at its maximum performance. A frequency response has an upper cutoff frequency and a lower cutoff frequency, which we call them FL and FH, or F1 and F2. So frequency response graph usually looks something like this. Let me draw it. And here we have an lower cutoff frequency. The upper cutoff frequency, sometimes we call it F1 and F2. Sometimes we call it FL and FH. And the area between this is the frequency response, or the bandwidth of the system. Anything out of this region is what we call a stop band. So this black region is a stop band. And anything inside this is going to be the pass band. Okay, so we have the stop band, we have this pass band. Obviously, stop band, any frequencies in that region would be stopped, would not be amplified, and anything in the pass band would be passed. The FL and FH regions are determined by the gain of the system. And when the gain reaches 0.7 of the maximum gain, at that spot, we have our cutoff frequency. So 0.7 is actually square root of 2/2 of A max, or 0.707, or what we call the 3 dB drop. So for example, if our maximum gain in an op amp is 20, when the gain reaches 14, that is our cutoff frequency. We would increase or decrease our frequency until we reach that 14 gain. So the way that we actually find cutoff frequency in a lab is we would give the op amp a standard input voltage, like 1 volts, for example. And we already know that the gain is 20. So for example, it's an inverting amplifier. R2 is 20, R1 is 1, so the gain is -20. So we would know that the maximum gain in this system is 20 or -20. And then we would slowly increase our frequency on a function generator until the output reaches 14 volts. So that would be our upper cutoff frequency. And then I would reduce or decrease the frequency until, again, my output voltage reaches 14, and that will be my lower cutoff frequency. Sometimes we don't have lower cutoff frequencies if we don't have a coupling capacitor. And therefore, in those cases, the cutoff frequency would go down to 0, and we would have DC response, because op amp could work in DC as a DC input, so we would have a DC response. Let me draw that one as well. So if we don't have any lower cutoff frequency, then the graph would look like this. We don't have an FL. Therefore, the frequency response would look like this. And this is what we called a low pass filter. So a low pass filter is usually a filter that doesn't have a lower cutoff frequency, so it passes all the lower frequencies. And you can see here, it passes from 0 hertz, and 0 hertz, by the way, is a DC voltage, up to an FH, which here could be 1 megahertz, 10 megahertz, and so on. So now the question becomes, why do some op amps have a lower cutoff frequency? Why do some of them don't have that lower cutoff frequency? Why some do and why some don't have it? The reason is that the cutoff frequency is determined by the coupling capacitor, and the coupling capacitor is the capacitor which is connected between the source and the input of a op amp. I use this terminology a lot before in electronics as well. So a capacitor is very good in passing an AC signal. This is not accurate theoretically, but it's good for demonstration. But if you have a DC signal, it's going to block that, okay? So AC signal is going to pass it, but DC signal is going to be blocked here. So if DC signal is blocked, then you can't pass it, then you're not going to have any output. So what determines the cutoff frequency, lower cutoff frequency, or FL, is actually this capacitor here. And if we don't have this capacitor, For a system that doesn't have this capacitor and is directly connected to Vs, like the lower one, therefore we won't have any cutoff frequency and the graph will look like this. But if we have this capacitor, then the graph will look like this. You have a lower cutoff frequency and the upper cutoff frequency. And this lower cutoff frequency, FL, is determined by this capacitor. The upper cutoff frequency, and I mentioned this in the internal design of a op-amp, we have these small capacitors which are between the pins of transistors. And those internal capacitors determine our upper cutoff frequency. Because those capacitors are built into the system and it's a manufacturing thing, we cannot change the upper cutoff frequency. But since the lower cutoff frequency is determined by this coupling capacitor, we can change the lower cutoff frequency easily by simply replacing this capacitor with a larger capacitor or a smaller capacitor, or completely getting rid of it. If I completely get rid of it, I would have the frequency could go down to DC. So if there's no coupling capacitor, the frequency could go down to DC. But there will always be an upper cutoff frequency because of the structure of an op-amp. But it's very easy to find. And the way that we find that is usually the manufacturer gives us the data sheet, and in that data sheet, we have something called the gate bandwidth product, and all the cutoff frequencies are also, the upper cutoff frequencies are mentioned over there as well. So the gain bandwidth product is what that determines our upper cutoff frequency, and it's usually provided by the manufacturer. So lower cutoff frequency is up to us and how we design the system, which capacitor we use, if any capacitor we use. But the upper cutoff frequency is a limitation of an op-amp as well. And we don't have any control of that unless we pick a different op-amp. So if we want an op-amp that has a wider frequency response and a bigger gain bandwidth, we have to spend more. Usually those op-amps are much more expensive. But lower gain bandwidth, like 741, they are pretty cheap. So you pay for what you get. Or you have to spend more on those. But there are different ways, again, to increase the gain bandwidth product, like using feedbacks, and I'll explain more about that. So because this is a first order system, we would have 20 dB drop per decade, or roll off of slope in the system, meaning we would have 20 dB, this is, by the way, 20 dB drop in the system per decade and increase in the frequency. And this is actually determined by, again, the op-amp itself. The gain bandwidth product for an ideal op-amp, again, you can read faster than I can. I'm just going to mention things that are not on the slide and the complementary information. So for a normal 741 op-amp, like the UA741, the gain bandwidth product is usually 1 megahertz. This is very important. And this 1 megahertz actually determines the cutoff frequency, the upper cutoff frequency for the system. We can change the gain bandwidth product by including a feedback, but adding a feedback has a trade-off. Adding a feedback decreases the overall gain, but On the other hand, it increases the gain bandwidth and the frequency response. Sometimes we need a broader frequency response. We would add a large feedback. Sometimes the gain is important, so we would add a small feedback or no feedback at all. Having no feedback, you would have very limited gain bandwidth or frequency response, but you would have extremely high open loop gain. So this is an example of comparing an open loop gain with a closed loop gain. The green graph that shows the closed loop gain and the red one shows the open loop gain. You can see for the open loop gain, the frequency response and the bandwidth is much smaller. Let's say this is 10 Hertz. But for a closed loop, I'm going to do a different color for the closed loop. So for closed loop, it's 10 kilohertz. For this open loop, it's only 10 Hertz. But the gain of the closed loop is much less than the, let's say this, gain AOL and ACL. So for closed loop, obviously the gain is much higher than, so for open loop, the gain is much higher than closed loop. So determining on the op amp, we have some power of over controlling the bandwidth, but again, that is limited to the op amp as well. If an op amp has limited bandwidth product to begin with, you would have limited bandwidth to work with at the end. And I would solve some practice problems on the gain bandwidth product and its effect on frequency response on different op amps, the 441 and the 741, which one of them is a slow op amp, and one of is a fast op amp with a high slew rate. So by knowing the gain bandwidth product and the gain, the associated break frequency can be quickly determined. For the inverting and non-inverting voltage amplifier, the F2 or the upper cutoff frequency is equal to gain bandwidth or A noise. A noise is the same in a non-inverting and an inverting amplifier. And for both of them, it's equal to 1 plus R2 over R1. So A for a non-inverting amplifier was equal to 1 plus R2 over R1. A for an inverting amplifier was negative R2 over R1. But A noise is, for both of them, it's the same, and it's equal to the gain of the non-inverting amplifier, which is equal to 1 plus R2 over R1. So to find the noise gain for any circuit, we will short all the voltage sources and open all the current sources. So we can use this equation to simplify and easily find our upper cutoff frequency in an accurate way. And as I mentioned, the noise gain is the same for non-inverting and inverting amplifier. The only item remaining for each source should be its internal resistance. At this point, simplify the circuit as required and find the gain from non-inverting input to the output of the op amp. So for a non-inverting amplifier, A noise and the voltage gain are the same, but for an inverting amplifier, we have to be careful. A noise is actually equal to 1 plus R2 over R1 in contrast to the voltage gain, which was negative R2 over R1. So let's solve some practice problem. I think this is gonna be it's gonna be easier to learn it using practice problems. So example number 1 and examples. Using a 741 op amp, what is the upper break frequency for a non-inverting amplifier with a gain of 20 dB? For a 741 op amp, the gain bandwidth product is 1 megahertz. Again, F2 is equal to, as mentioned, gain bandwidth over A noise. I'll give you 5 minutes to think on this and then. Does anyone have the answer? 100 kilohertz. 100 kilo. Who else has
I got 50K.
50K? Okay. Anyone else? Okay. So converting the 20 dB into ordinary form yields a gain of 10. And F2 would be gain bandwidth over A noise would be 1 megahertz over 10, which gives us 100 kilohertz of the upper cutoff frequency. Twenty log of, do you remember dB? 20 log of 20. And you had some, I think, practice problems on converting dB to in the first homework. So what happens is here we're gonna have the gain is actually constant and then it suddenly drops for that.
And what's this formula?
20 log of 20 dB. Okay, so in example number 2. Sketch the frequency response of the circuit. This is an inverting voltage amplifier. And first you need to find the gain. And Then you have to find the upper cutoff frequency, which is the gain bandwidth over A noise. Okay, did anyone solve the problem? Perfect, yes. So first thing you need to find A noise, which is equal to 1 plus RF over RI, which is 1 plus 10K over 2K gives us 6. The gain itself is negative because it's a inverting amplifier. The input is connected to the inverting part. It's going to be equal to negative RF over R1 or RI, which is going to be negative 10 over 2, gives us negative 5. In other words, it's 14 dB. So the gain is at 13 dB. And this is actually the question that I had last year's exam, very, very similar to this. And now we have to find the cutoff frequency. define this frequency response. So the cutoff frequency F2 is gonna be equal to gain bandwidth over A noise, which is gonna be 1 megahertz, over A noise, which was 6, gives us 167 kilohertz. So what about the lower cutoff frequency? We don't have any lower cutoff frequency because we don't have any coupling capacitor. Therefore, the frequency response could go down to 0, and this actually acts like a low pass filter. Let's go to another example. In this example, we want to determine the maximum acceptable F unity. And by the way, F unity is actually our gain bandwidth product. We sometimes call it, as mentioned, F unity. For the circuit of the following figure, if response should exceed at least 50 kilohertz. So we want the cutoff frequency to be at 50 kilohertz. Do you need more time, or have you solved it?
2.5 megahertz.
I'm sorry?
2.05 megahertz.
Okay, 2.05 megahertz. So the problem is, if it's 2.05 megahertz, we can't use a 741. A 741 op amp has a limitation, and the limitation for the op amp is 1 megahertz. Therefore, we have to use a faster op amp for that. So That's correct, yes. So first we want to find A noise. By the way, this is a non-inverting amplifier. And since it's a non-inverting amplifier, the voltage gain and the noise gain are the same. So A noise would be 1 plus RF feedback over RN, which is 1 plus 20K over 500 gives us A noise of 41. Then the F unity or gain bandwidth product would be F noise times F2. Again, because F2 was, my pen stopped working, but F2 is equal to gain bandwidth product, A noise therefore. And A noise is, and F unity is gain bandwidth product. So it's gonna be 41 times 50 kilohertz gives us 2.05 megahertz. So again, as mentioned, the 741 isn't fast enough. It has a limitation of around 1 megahertz. Therefore, we need to use a faster op amp, which we use a 411. But there's another way, a different way there's another, I can say, loophole to bypass this limitation. And that is to use multi-stage op amp. So if we don't have a fast enough op amp with 741, and if we want to design something like that, and we don't have access to a fast op amp, another way to overcome this issue is to use multi-stage op amps. So for this example, we would assume that all stages use a 741. What is the system's gain and the upper break frequency? And the gain bandwidth product, just give me reset my and so for a 741, the gain bandwidth, or in other words, if unity is equal to 1 megahertz. So for this example, what I want you to do is I want you to find F2 and gain for each of these stages. So we have 3 stages. And I want you to find F2 and gain for each stage. Okay, what is F2 for the first stage? First of all, what type of amplifier is it? Is it a non-inverting or an inverting amplifier? It's a non-inverting amplifier. What is A noise for the first one? It's 14/2, which is 7 plus 1, it's 8. So 1K/8. It's gonna be what? I'm sorry, 166, something like that. Yes, 125. Yes, I'm sorry. Yeah. Second stage, gain, it's an inverting amplifier. Its gain is -2, but its A noise is 3. 1 plus 2 is 3. That is gonna be 1 megahertz over 3, it's going 333 kilohertz. This third stage, it's a non-inverting amplifier. The gain is gonna be equal to 4. A noise is also 4. The upper cutoff frequency is gonna be 1 megahertz over 4, which is 250 kilohertz. So we are now left with 3 stages. One stage has a upper cutoff frequency of 125. One has one with 333 and one has one with 250 kilohertz. What is the upper cutoff frequency of the total system? No, that's not how it works for cutoff frequency. Cutoff frequency is limited by the stage that has the lowest cutoff frequency. Because that is the limiting factor, okay? Let's put it this way. Imagine you wanna move a cargo from here to Houston. The first leg is with train and the maximum speed is 90. The second leg is with a car, the maximum speed is 120, for example, and the third one is with the airplane, maximum speed is 900. Your limit is the limited of the slowest part, you know. You can't imagine that the whole trip would go with 900 miles per hour. It was always limited with the lower speed, which here is 125 kilohertz. Maybe that wasn't a great example because you would average the speed here, but I'll explain more about this in the next class. But you're always limited to the lower speed. Anything above the speed would be cut off by this stage. So this is gonna act like a filter for the rest of it. So what we're gonna have is this. We're gonna have one stage is 120 kilohertz. The second stage is 333, and the fourth stage is 250. So any frequency that say it's here is gonna be already cut off by this stage. So anything above this 125 is not gonna work. So how can a multi-stage amplifier help us by increasing the overall frequency response? I'm gonna explain that in the next class. When we have all the stages are identical with the same frequency response, then that's gonna help. It's not gonna multiply the frequency response, but it's gonna help and boost our frequency response. Okay, thank you so much. We are out of time for today. We're gonna have our exam probably, I would say, on I would send an announcement for online students, but for us, it's gonna be probably on 14th, if it's okay with you. 15th. 15th is the next Tuesday, am I correct? Yes, so on Thursday, we're gonna have a review session, and I will post another announcement about that. For online students, I've already sent them an announcement. It's a different time for them. Okay, thank you so much, and I'll see you on Thursday. Yes, that's the upper break frequency, yes, and the lower break.